like she pays attention. My class is so important for her.
We're going to be looking at prime cuts of numbers, prime numbers in 2.3. First, I'll go over a couple of questions that I got emailed though. So I got emailed Mindscapes 10 and 21 from section 2.2. So in Mindscape 10, we suppose we build a sequence of numbers using a method of adding the previous two numbers to build the next one, like we did with the Fibonacci sequence. But instead of starting with 1 and 1, we start with 2 and 1. And you put them in an order, okay? Don't put them in numerical order. Put them in the order they're said in the problem. Then we go on from there, adding just like with the Fibonacci numbers. So 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 4 is 7. And you can continue on in that fashion. Does anybody have any questions on that question? Okay. Then let's go on to 21. We have people playing Fibonacci Nim, and we have a couple of moves already played. So we're going to follow that through. You probably start with a different number of sticks on your problem. They're all a little different. Well, most of them are a little different. Mine starts out with 15 sticks, and I start by taking 2 sticks, and then the friend takes 2 sticks. So I'm going to write that down and work on it on paper. So I take 2 sticks, and the friend takes 2 sticks, and that means now there are 11 sticks. Then the question is, how many should I take? So we're taking the strategy that we took in class so that you can win at Fibonacci Nim. So we'll need the Fibonacci numbers written out at least past the 11. So we think of the 11 as a sum of non-consecutive Fibonacci numbers. Remember, we start with the biggest Fibonacci number we can. So you look in the list, 11 falls between 8 and 13. So I'm going to write the 11 as a sum starting with the 8. 11 minus 8 is 3. So I still have 3 more sticks to get. 3 is the next Fibonacci number too. So I'm going to say 3. So I've written the number of sticks left as a sum of non-consecutive Fibonacci numbers. Does anybody remember then how many I pick up once I've done that? Yes?
3.
Good. Yeah. Pick up the smallest number in your list. So that works because my friend picked up 2, so I'm able to pick up any number between 1 and 4. And 3 does fall between 1 and 4, and if I continue with that strategy, then I can win. Anybody have any other homework questions? I wanted to take your attention to the school's website for free tutoring. So go to the school's website, and then after the uwgb.edu, put /tutoring. And here's where you can find how to go about getting free tutoring. So you can stop at the library, CL207, so that's the main floor of the library, and you can walk in there and get help with tutoring. Actually, you would set up an appointment for help with tutoring. The other thing is, if you're an online student or you don't want to come into campus that day, you can use BrainFuse and get tutoring online. Okay. But we're also going to see about a study group, and so Juan is one of our tutors for this class. He's given me a list of hours that he's free to tutor. So the hours that are grayed out, he is not free. Online students, you can email me where to put tally marks if you're interested, because what I'll ask you to do is go through and put tally marks in the times you would be interested in tutoring. So some of these problems that we go over are pretty tricky, and you might need to practice on a regular basis. If that's the case for you, if you're feeling kind of lost in some of these areas, you should go to the tutors. That's their goal, is to get you through that quiz. The tutors will take the review sheets, or you can bring your own review sheet that you can print off a Canvas yourself, and they'll go through those problems and make sure you are ready for the quiz. So I encourage you to do that, especially with some of the hard proofs that we do. So you can see the tutor and repeat that over and over until you get it down. Anyway, you can do that in a study group too. That will be the focus in a study group, getting ready for the quiz. So if you're free Tuesday mornings, for example, put a tally mark in all these sections. If you're free Wednesday nights, put a tally mark in all of those sections. And then Juan will take this and decide when he will offer a study group. So I'll send that around, and online students, you can email me your choices if you have some. Thank you. Well, we've been looking in section 2.3. The life lesson in that section is that simple observations often have deep consequences. So it's millennia ago, actually, people noticed that some numbers are not evenly divisible by others. And that gave us the idea of prime numbers, which are the building blocks of all the numbers. So we're going to continue looking at those prime numbers today. We were coming up with a proof to prove that there is no largest prime. This is one of the harder things that we do throughout the semester, so try and put your thinking caps on if you were kind of drifting away there. We're going to prove there is no largest prime, so we had come up with a strategy. And to demonstrate that strategy, I was just saying, well, how about we prove there's a prime larger than a particular number? So let's do that. Find a prime. Find a prime. A prime number larger than 6. So eventually we want to be able to find a prime number larger than any number, larger than 1,000,000, larger than 100 billion, larger than any number. But for now we just start with finding a prime number larger than 6. So we created a number that was not going to be evenly divisible by 2, 3, 4, 5, or 6. In fact, if you took the number we created and divided by 2, 3, 4, 5, or 6, there was a remainder of 1. Does anybody remember how we created this number that would not be evenly divisible by 2, 3, 4, 5, or 6? Good. And what did we multiply? So we multiplied 2, 3, 4, 5, or 6. Now this number is evenly divisible by 2, and by 3, and by 4, and by 5, and by 6. So how do we make sure it wouldn't be divisible then? Add 1. Good. Okay. So now, whatever this number is, if you try to divide by 2 or 3 or 4 or 5 or 6, you get a remainder of 1. It's not evenly divisible. So let's take out our calculators and see what that number is. And I'm going to ask you to do this in a little bit with another number, okay? So let's make sure you get the hang of it. I think understanding this idea will help you as you learn the proof. I mean, you can just always memorize what we write down, but it's certainly much more satisfactory to know what we write down, what it means. So we found the number 721 like this, and if you divide 721 by 2, it's 360, remainder 1. If you divide by 3, I don't know what that one is, but I know it has a remainder of 1, and you can divide by 4 or 5 or 6, and you'll have a remainder of 1. However, is this prime? Did we find a prime larger than 6 in the number 721? Well, I know it's not divisible by 2, 3, 4, 5, or 6, so I might as well go right to 7 and see if I'm divisible by 7.
Yes.
Is it divisible by 7? What do you get?
103.
7 times 103. Thank you. And 103, today I brought my list of the first 100 primes, so I can save a little work here. First 100 primes, and 103 is prime, so I don't have to keep factoring there. Okay, but you notice that the prime factorization has only prime numbers larger than 6. So we constructed this number in such a way that if it didn't turn out to be prime itself, the only prime factors that it would have would be primes larger than 6. It was actually Euclid who gave us this idea 2,000 years ago, more than 2,000 years ago. And it's a very clever and elegant idea to make sure that none of these other numbers will divide evenly into the 721 because of adding this 1. So when we're searching for a prime number larger than 6, we didn't find it in this big number. But if the big number itself is not prime, well, it has a prime factorization. And the prime factorization would only have primes larger than the 6 in it because of the way we constructed this. And so there we find a prime larger than 6. In this case, it was 7, so not that much larger, but it is larger than 6. Okay, so I'm going to ask you to do something similar. We'll just hop up 1 unit to 7. Find a prime number larger than 7. Okay, so go through the same process, please, of finding a prime number larger than 7. And don't just say 11. Use this process that we've been using. And then I'm hopeful that it will help you when we go through the proof to understand the proof. So I'll walk around if you're stuck, and Nicholas can walk around too, and we'll help you. To actually factor this, you might want to go to this website. Here, I'll show you a website. This is a great website for doing math things. It's wolframalpha.com. So this is a great website for doing, I think I showed you on my phone. This is a great website for doing factoring. So you can factor whatever you get here, in case it's too big to factor by hand. So I'll walk around and see how you're doing. Please raise your hand if you're stuck. Okay, yeah, that's the number I was looking at. I will see how you're doing. Now, if you forgot and started trying to factor at 2, 3, 4, 5, and 6, hopefully you found out those don't work. So we had the process that we used before. So we're in the middle of deciding if this number is prime or not. So we made this big number, and is it prime? Did anybody find a way to factor it? Let's check and see. So I'll use the wolframalpha.com. And it is 71 times 71. We'll just verify that, right? Sure enough, 5,041. So The number that we made, this big number, is not prime. However, the prime factorization has only primes in it larger than 7. So the 5041, the big number we made, did not happen to be prime this time, but the prime factorization had only primes larger than 7. Because 2, 3, 4, 5, and 6, and 7 will all have a remainder of 1 if you divide them into 5041. Okay, well that gives us a strategy. Instead of just picking this prime number, finding a prime number larger than 7, we want to find a prime larger than any number. So that's where our proof comes in. So you'll see on the quiz a question like this. Prove that there are infinitely many primes, or it might say prove that there is no largest prime, because that's the same thing. Proving that there's infinitely many prime or that there's no largest prime, it's the same thing. So here's the actual proof that you would need to be able to recall, or you can write notes to yourself on your 3x5 card. We'd say, let M be any natural number. Let M be any natural number. So M stands for something like our 7 or our 6 or our 7 billion or our 7,892,000. M is any natural number. We need a prime larger than M. We need a prime larger than M. So we're going to always be able to find that next bigger number that's a prime. So let's make B for big, right? Let's make the big number that we've been making. Let's make B 2 times 3 times 4 times ... times M plus 1. So let B, so B is for big, B equal 2 times 3 times 4 times ... times M plus 1. Well, it's important that B is big, so we have to say that in our proof. B is bigger than M. Okay, B is bigger than M. It's at least bigger than M by one number because we add 1 on. So it's a bigger number than M is. B is bigger than M. If B is prime, we are done. Okay, if B is prime, we are done. We will have found a prime number bigger than M. If B is not prime, it has a prime factorization. If B is not prime, it has a prime factorization. Because that's what it means not to be prime, right? It has a prime factorization. Okay, so if B is not prime, it has a prime factorization. Let P be a prime factor let P be a prime factor of B. Let P be a prime factor of B. So I have a prime factor of B, P. P is not 2, 3, 4, comma, dot, 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 comma, M. P is not 2, 3, 4, comma, dot, 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 comma, M. Why is P not 2, 3, 4, comma, dot, 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 comma, M? Why isn't P in this list of numbers?
It's too small.
These are too small. Can anybody tell us more about why P isn't in that list? Yes.
Because we use that list to get B, and P would be a factor of B, so it wouldn't be in that list.
Good, because we use this list to make B, and these don't divide evenly into B, because we used this list and added 1. So P is not in that list. Let's see if we can write that with out so much explanation. Okay, so P is not 2, comma 3, comma 4, comma 5, etc. up to M because they don't divide evenly into B. Okay? They don't divide evenly into B. They have a remainder of 1. So P is a prime larger than B. So P is a prime larger than B. So a proof is an irrefutable sequence of steps that each step can't be challenged. For example, look at this step. B is prime or it's not prime. You know, those are the only two options. There's no other options. B is bigger than M. B is bigger than M because you added 1 here. Once you've found the prime factorization and you picked out a number, P is not in that list because we made sure we constructed that number B so that none of those numbers divide evenly. Yes, Nicholas?
Last line should be P is prime larger than M.
Oh, thank you very much. Thank you. Good eye, good eye. Okay, P is a prime larger than M. That makes more sense. In fact, let's take our letters and compare them with our last example so you can think about this later and make sure you understand what everything stands for. So here's our last example we looked at. So we're finding a prime larger than 7 here. Here we found a prime larger than M. Here this 7 was the M in the proof. And then we made our big number. So this number 5041, that was our big number. And then we had our big number was either prime or not prime. In this case, it was not prime. So in the prime factorization, we have these numbers that in our proof we call P, 71. So P is a prime factor of our big number, but it's not in our list here because these numbers do not divide evenly into 5041, but the prime factors of 5041 divide evenly. So this is a beautiful, elegant proof that we have from Euclid. And the key is finding this number. Once we see this number, we're like, oh, of course. But to come up with that kind of elegant simplicity to make that number, that takes a lot of thought, a lot of genius work there. We're going to look at some other theorems in this section. This is one, though, to memorize. The other theorems you won't have to learn the proofs for. Okay, so make sure you know that for the quiz. Does anybody have any questions on that before we go on to these other theorems? So we are looking at the mostly true story of Fermat's last theorem. So the only thing that the author filled in are the details, because well, you'll read when I read it, you'll know what he filled in. Okay. It was a dark and stormy night. Rain pelted the wavy window pane. Wind seeped in through cracks in the window frame. A candle flickered uncertainly in the cold breeze. The year was 1637. Pierre de Fermat sat in the great chair of his library poring over the leather-bound Latin translation of the ancient tome of Dianthus Arithmetica. He concentrated intensely on the ideas that Dianthus had written 2,000 years before. During those 2 millennia, whole civilizations had risen and fallen, but the study of numbers bridged Fermat and Dianthus, spanning centuries and even transcending death itself. As the night wore on, inchoate ideas, at first jumbled and ill-defined, began to weave a pattern in Fermat's mind. He gasped as insight and understanding began to take shape. He was seeing how the parts fit together, how the numbers played on one another. Finally, it was clear to him. On that fateful night in 1637, he wrote in the margin of Dianthus Arithmetica the statement that would make him famous forever. He wrote in Latin, "It is impossible to write a cube as a sum of 2 cubes, a 4th power as a sum of 2 4th powers, and, in general, any power beyond the 2nd as a sum of 2 similar powers. For this I have discovered a truly wondrous proof, but the margin is too small to contain it." So this is Fermat's last theorem. Has anybody heard of it before? When I was in high school, it was an open question, so my calculus teacher told us that this might be something we would want to go on and study and be able to prove. There was $1 million prize for this, the answer to this question at that time. It's called Fermat's last theorem because Fermat had a habit of writing down these theorems and then not including the proofs. So he'd write down the theorems and send them to his friends across the continent and across England, and they'd say, "This is great, Fermat, I believe you, show me the proof," And he just didn't always include the proofs. So it's Fermat's last theorem to be proven. So all these other theorems that we just knew the theorems but didn't have the proofs behind to validate the theorems have been proven until this one. This one remained for more than 350 years. And then in my lifetime, it was proven by Andrew Wiles. So this proof was quite intensive. He took 10 years to develop it. Mathematicians work on proofs for many, many years at times. So it took more than 10 years to develop, and when he presented it, it took 2 days at the math conference to present. So he went to a math conference to present the proofs, and the audience hung on their seats checking to see, did he make an error, did he make an error? Kind of like, Nicholas, did you make an error? Make sure you don't have any errors, because that's what mathematicians do. They want to challenge your proof and make sure it is valid. And it was. It was. They went home, and the mathematicians went home and conferred together to make sure everything was right, and it was. And so he proved that over 350 years later. So Wiles' proof took over 130 pages to write, much longer to present, and it is undoubtedly not the proof that Fermat was thinking of, because it contains areas of mathematics that were not even investigated at the time of Fermat or even known about. So some other mathematicians are no doubt working now to find, well, what was Fermat's proof? Now that we know that it is in fact a true theorem, what was Fermat's proof? We're going to just make sure we understand the proof and know that it's proven. So we have 3 different ideas in this last section of this chapter, of this section. The first is Fermat's last theorem. And what is it saying? Let's look at it again. It is impossible to write a cube as a sum of two cubes, a fourth power as a sum of two fourth powers, and in general, any power beyond the second as a sum of two similar powers. Okay, so I'll get my notes on that page by folding it up. A cube as a sum of two cubes. So here's my cube as a sum of two cubes. A fourth power as a sum of two fourth powers. Or in general, any power beyond the second. So a to the fifth plus b to the fifth equals c to the fifth. These are all impossible. And I'll put a dot, dot, dot after. So Fermat knew, and Andrew Wiles gave us the proof, that this is impossible. Now he came and thought of this as he was reading Diamphatus Arithmetica. What do you think was in Diamphatus Arithmetica that made him think of this, that made it even occur to him as a question to consider? Does this look familiar to anybody? What does this look like? Yes?
A squared plus b squared equals c squared.
Good. A squared plus b squared equals c squared in a right triangle. So this we know is true. Pythagorean gives us one proof. So that we knew is true. But this other, Fermat figured out, is impossible. So the highest exponents you can get in this kind of a pattern is 2. It will be impossible to find any cubes. So what he's saying is that here there's lots of numbers that a cubed plus b cubed equals c cubed. For example, 3 squared plus 4 squared equals 5 squared. Because that's 9 plus 16 equals 25. These are impossible. There are no numbers like 3, 4, and 5 that make those true. It's just impossible. So this has been proven, and on quiz 3 you will need to know that Fermat's last theorem has indeed been proven, because we're going to look at some other theorems that have not been proven or disproven. So let's look at those next. I'll put this notebook down so it can write on paper. So what we see next are the twin prime question. The twin prime question says, are there infinitely many pairs of prime numbers that differ from one another by 2? For example, 11 and 13, 29 and 31, 41 and 43 are examples of twin primes. So those are two primes that differ from one another by 2. Are there more? Well, there are more, but are there infinitely many more pairs of twin primes? So this is called a question because no one knows. No one's been able to prove that there are an infinite number of pairs of twin primes, and no one's been able to prove that there's not, that at some point you come to the last pair of twin primes. So you'll need to know that this is an open question, and I'll write that in my notes in a little bit. You'll also need to be able to find twin primes. So you yourself will have to come to the quiz with a twin primes in mind. So here's a list. You can look from the first 100 primes and pick your own favorite set of twin primes to have ready for quiz 1. Does anybody see a set of twin primes that we didn't list in the textbook? So they differ by 2. Where's 2 primes on that list that differ by 2? Yes?
197 and 199.
197 and 199. Perfect. Okay, so that's an example of twin primes because they differ by 2. So everybody needs to have their own set of twin primes. Let's write that down, okay? Twin primes For example, 197 and 199. You should come up with your own example, okay? Everybody shouldn't use my the one example. And then this is an open question. It hasn't been proven, and it has not been disproven. Whether there is an infinite number of twin primes or not. So you don't have to be able to quote the twin prime question. I will write the twin prime question and Fermat's theorem right on the quiz. In fact, I'll also write this next one, the Goldbach. What is it called? The Goldbach question. So the Goldbach question says, can every positive even number greater than 2 be written as the sum of 2 primes? Can every even number greater than 2 be written as the sum of 2 primes? So let's pick an even number and see if we can write it as the sum of 2 primes. So we need an even number. So someone provide an even number, please.
4.
4? Okay, and I heard another one. What was the other one?
12.
12. Okay, great. Okay, so we have 2 even numbers. And the question is, can every even number bigger than 2 be written as the sum of 2 primes? Now remember, 1 is not a prime, so don't use 1 in your sum. But we need to write this as the sum of 2 primes. So that kind of narrows it down here. Since 1's not a prime, that leaves us with 2 plus 2 for the 4. How about 12? What 2 primes can you add together to get 12? Sure, 5 plus 7. There may be more than one way to do some of these, okay? So that's an open question, and it says question, so that kind of helps you to know that has not been proven, and it's not been disproven. We don't know if there's some even number that cannot be written as the sum of 2 primes. So this you would think would be easy to disprove. You'd think you would just go through your even numbers and keep checking. Can I add this? Can I write this as the sum of 2 primes? Can I write this as the sum of 2 primes? And that eventually you would get to an even number that cannot be written as the sum of 2 primes. So disproving this one may be easier than proving, but it must not be very easy because nobody's proven it yet or disproven it. So on the quiz you'll need to know that this is proven. The Fermat's theorem is proven. These other 2, twin prime and Goldbach questions, have not been proven or disproven, and you'll need to be able to give an example of each when you see them written down, okay? We're going to go on then. Does anyone have any questions before we... Oh wait, no, I wanted to show you something I thought was kind of interesting. So this is a discussion on the conversation, and it's about mathematical method, which I talked with you about briefly. Any mathematical method used at school or work or anywhere was figured out at some point by a mathematician. Another mathematician may have proven that it always works, and another may have worked out how to use the method in the real world. Someone else might then have shown that it's not a very efficient way to solve larger problems and develop a different approach instead. Now as we look toward prime numbers, here's an example of such a recent result. It deals with the distribution of prime numbers, like 7, 11, 23, or 37, which you cannot divide by another natural number other than 1 or themselves. We found prime numbers as large as 22 million digits, and researchers are still looking. As it turns out, prime numbers slowly but steadily appear less frequently. They thin out among the larger numbers. A breakthrough in 2014 showed that no matter how high we go among the numbers, we will always find two primes that are closer to each other than some constant number. Okay, so for example, the twin primes were 2 apart. He's saying that we'll always be able to find some number that will have 2 prime numbers that close to each other. That number was initially a whopping 70 million. That might not seem very close, but the fact that we could identify a finite number was an important breakthrough. Other mathematicians then set out to reduce this value, and the best I am currently aware of is a much more manageable 246. So he's saying there's always going to be primes that are within 246 of each other. Not that all primes are within 246 of each other, but there are pairs of primes that are within 246 of each other. Underlying all of this is one of the fundamental truths about mathematical research. The applications of mathematics might change with scientific progress, making some mathematical topics more useful at times than others. But because mathematical results are based on logical deductions alone, they actually never become wrong, never get obsolete, and never truly get old. They are just waiting for the right application to come. Now, this is one of the things I love about math, that it's once it's been tested and solid, it's true. For example, when I was in high school, when they had covered wagons and no cars, no, I'm just kidding. When I was in high school, the big fear that would be on the front of Newsweek and Time magazine on a regular basis was global cooling. Okay, we were all going to be in the ice age by the time you kids were born because of our use of carbon in the world. Then you saw that change to global warming, and now it's called climate change because it gets warmer and colder. Okay, but math doesn't do that. Math stays constant. This class ends at 12:35, so we still have a little bit of time. So we're going to actually look at another idea here in the next section. We are going on to section 2.4, and I'd like you in your groups to answer this question that the author starts the class with. Today is Friday, February 7th, 2020. On what day of the week will the 4th of July fall this year? Now, don't look on Google, please. Don't. Okay. Don't try not to use previous knowledge if you happen to have a birthday that day. Okay, try not to use that. But I'd like you to use math to figure this out because it's going to help us in our work in section 2.4. So, you'll probably need to know how many days are in each month if you do not. So when I was in school, you learned a little rhyme. 30 days has September, April, June, and November. "30 days has September, April, June, and November. All the rest have 31, except for February." So use that idea and see what day the 4th of July will fall on. So I'd like you to work in groups. So if the first row could turn around and work with the second row. I don't think the third row can turn around and work with the fourth row, but you can work in groups there, please. And Nicholas and I will come around and help you if you get stuck.
So the 7th is a Friday. The 4th was on minus.
I guess, do you two just want to work together?
Yeah.
Okay.
So July will have 31 days.
And you're working together? You two are working together?
Right.
And you four are working together?
Yeah. So 31 days for July. And today is a Friday.
Okay,
So
so we're in July.
we're in February. And February does not have 31 days.
February 29, I mean, leap year.
14, you're on March
And it's
27th.
not leap year.
Yes, it is.
Oh, it's leap year this year? Okay, so it'd be how many
So plus 7 would be
29 minus 7 is
30,
22. So there's 22 days left.
39, so it'll be the 3rd of April, plus 7 is 10, plus 7 is 17, 7 is 24, plus 7 is 31.
God.
31 days.
Okay,
July 1st.
March
June.
has 30 days.
A week is 7 days.
So hang on, June 29th.
That does work. You can remember that well. Okay, now try it right now and see if it confirms.
Is June 30 days?
30, yeah.
So 30th would be a Saturday, or like Monday, 3rd.
July. So 31 minus 1.
Cool. It's Wednesday.
I gotta get to July 4th, so 4 days. So there's
22 days left. Plus, so you just add those up.
We just kept adding 7 days total.
Okay, like 1,000 days.
Yeah. But we tried to figure it out.
How many days are divided? Because there's 7 days a week. Yeah, so you divide by 7.
Okay.
Well, let's think of it.
okay. So how many weeks are there?
Weeks, there's 4 weeks per month.
That's a little bueno.
1, 2, 3, 4, 5. So if there's 4 weeks per month. 4, 4,
1, 2, 3, 4.
there's about 5 to 4.
I'm just adding the 7 days.
Depending on if it has 30 days, it's gonna be 5 weeks. Maybe.
Okay, so we're at February 7th. Today is Friday. A week from now, so
He doesn't make them anymore.
I'm just hard. I hate time.
So do I. So a week from now would be the 14th, which would be a Friday.
Would be 21.
21.
And another week would be 28.
28. And there's how many days this month?
Oh, so you went through
Pretty
5
bad.
weeks? Yeah. Okay.
There's 22 days left.
That was pretty fast paced.
Wait, just leave here. How many days are this month?
29.
I see a couple groups have it. Let's work together.
I do.
This is where I'm done.
Blue, I love I just study it and know how to do it.
So basically, you're taking out groups of 7, right? Okay, so one way to do that is to add up the days in the month yet. And I've seen several people doing that. So if we're adding up how many days of the month yet, there's 22 days left in February because it's a leap year. March, 31 days. April, 30 days. May, 31 days. June, 30 days. July, we only want to go up to the 4th because we want to get to the 4th of July. Did anybody get 148? Is that right? Okay, thanks. 148. And then taking out groups of 7. So some of you took out groups of 7 by counting through, and that's certainly a way to do it as well. I'm going to take out groups of 7 this way because we're going to use modular arithmetic, and this will be good practice for that. So you'd put in your calculator 148 divided by 7, and we get 21 point something. So 21 is how many weeks I can take away. So how many days does 21 weeks make? 21 times 7 is 147. So 21 weeks you should have taken away as you were counting through your weeks, and that leaves you one more day. So today's Friday, 4th of July will be on a Saturday. So if you figure that out, pat yourself on the back, okay? Okay, so we're taking out groups of 7, and that's the idea behind modular arithmetic. So we will be seeing more of that in section 2.6. I'll see you on Monday. Have a good weekend.
Oh, that makes sense. 22 is
This adds it. What about the goal box thing that we were supposed to post like canvas?
Yes, your class activity was to take a picture of the Goldbach picture. The Goldbach, here it is. The Goldbach question is your class activity. So take a picture of that. Okay. Or if you want, you can come up with your own numbers instead of those. Thank you for asking.
Yeah.
Thank you.
I just noticed that it was like due this weekend and I'm like, oh,
Thank you.
Oh, which one? Oh, which one do I want? Never.